All right, so quantum dynamics, that's what we were discussing last time. Okay, and it's governed in one formulation by the Schrodinger equation. In today's lecture, we shall come across another formulation of quantum mechanics in which the central equation is not Schrodinger equation, but Heisenberg's equation. So Schrodinger equation is the analog of Newton's equation for quantum mechanics, is the analog of Newton's equation, but for quantum mechanics. Newton's equation is second order in time, but Schrodinger's equation is first order in time. Okay, so, and there are important differences. Well, Schrodinger equation is an evolution equation. Newton's equation is also an evolution equation. Schrodinger's equation is a kind of wave equation. Newton's equation is not a wave equation. So this equation is known as the time-dependent Schrodinger equation. Okay, so there is so I'm reviewing a little bit of what I did last time because I think I went a bit too quickly last time. So this equation can be solved, but if you can solve the Hamiltonian eigenvalue problem. So, and that's because the Hamiltonian plays an important role in the Schrodinger equation. So for the purpose of this lecture, we can assume that the Hamiltonian is time-independent operator, that H does not have, it doesn't have an explicit, it doesn't have an explicit time dependence. Okay. Later in the course, we shall see how to incorporate time dependence in the Hamiltonian. So what we want to show is that if we can solve this problem, we can find the eigenvalues and the eigenfunctions of the Schrodinger equation at some given time t, then we can solve the whole problem. And this is based on the fact that if we have a Hermitian operator, so if you have a Hermitian operator, say in this case H, then its set of eigenvalues, they constitute a complete basis for a Hilbert space. Means that any state psi of t at say some given time, say let's give, say let's take the time to be 0. Any state psi at time t equals to 0 can be expressed as a linear combination of the energy eigenstates. Okay, so this is an assumption we have about our Hilbert space, is that given a Hermitian operator, if we have its complete set of eigen vectors, we can express any state as a linear combination of these eigenstate. So knowing a state means knowing these guys and these coefficients, right? And these coefficients, so these complete set of eigenvectors are assumed to be orthonormal. What does that mean? That means that if you take psi m and take the bracket inner product with psi n, then it's 0 unless m is equal to n. Okay. So using that, we can see that psi of m, if I take the inner product with psi of 0, that gives me am, okay, the coefficient. Okay, so now suppose that we have solved this equation for a particular time, say t equals to 0, okay? So we know, and so we know psi at given time t equals to 0, it is a sum over a linear combination of psi m0. And if this solves the Schrodinger equation, this also solves the Schrodinger equation. Why?
Linearity of the Schrodinger equation.
Right, because it's a linear equation, right? Okay, so now if I look at the Schrodinger equation, but instead of a general state, I consider the eigenstate of the Hamiltonian operator, then the Schrodinger equation becomes this. This is the eigenvalue. On the right-hand side, I'm inserting the eigenvalue. So, this is basically what we are trying to solve. With the boundary condition that at t equals to 0, this state is, with the boundary condition that this state is equal to this state, okay? So now we can solve this equation. It's a very easy equation to solve. It's just given by psi of t is given by e to the power minus I em t over h bar psi of t0. And this is an important result that you should always remember, is that if you have an energy eigenvector, then its evolution is given just by a time-dependent phase factor, which is given by this, okay? But this is only true if h is time-independent, okay? So what is going to be the general state psi of t? So psi of t is going to be given by summation over m am psi m of t. And therefore, these guys are nothing but e to the power minus I em t over h bar times psi m 0, okay? So we have established that if the solution of the Schrodinger wave equation for any arbitrary psi of t can be given in terms of these coefficients and the energy eigenvalues exponentiated in this particular way times the energy eigenfunctions or energy eigenstates at a particular time, which we can call t0, t equals to 0. Okay, so this is the general solution to the Schrodinger wave equation. In other words, if you can solve the energy eigenvalue problem for your Hamiltonian, which is, say, time independent, then you have solved the problem. Okay, so sounds very easy, right? Of course, finding these energy eigenfunctions is not always an easy thing. Okay, so this equation allows us to express the time evolution in a more abstract way. And before we do that, let's just observe this thing. If H acts on, say, psi m, we get Em psi m0, right? If I apply H again on this equation, I get on the left-hand side H squared acting on psi m, but this thing is just a number, so H will commute with this. So H will act on this thing again and give me another factor of E. So on the right-hand side, I will get Em squared. In other words, for any integer value power of H, I can write this. Do you agree? So if I have some function of H, which is, say, a positive power series, so n goes from 0 to infinity, and we have some coefficient, say Cn, and H to the power n, then if I apply f of H on psi of m of 0, then the H just gets replaced by E in the function, right? So on the left-hand side, it's a formal power series given by this. On the right-hand side, this is a function. That is a number, right? So now we can use this observation and to this equation. Now here we have a power series. So what we can do is that we can replace that by, say, psi of t is equal to sum over m am e to the power minus I, and there where we're em, now we have h, t by h bar. And this is acting on psi of 0. So this is an operator. There should be an m here. But this operator does not depend on m. So we can take it out of the summation. Then we can write this as e to the power minus I, ht. Let me not forget this. I'm going to forget the hat often. And it should be clear from the context which is an operator and which isn't. And so there is m, a of m, psi of m0, and this is e to the power minus I, h, t by h, psi at 0. So if I denote this operator by u of t, it's e to the power, so this is the definition of e of t, e to the power I h of t by h bar, then we see that psi, any arbitrary state at time t is given by the action of u of t on psi at time 0. And this operator is known as the time evolution operator. And it evolves the system forwards in time. So if you apply u minus t on, say, psi of t, then you will get the system evolved backward in time. Okay? So this is very important that in quantum mechanics, the time evolution operator can evolve both forward and backward in time, just as in Newton's equation, right? So so this is an information preserving action. You know, it's not like thermodynamics where, you know, you can't go back. if for irreversible systems. So U of t, it's by definition, it's a unitary operator. Okay, so this is something I showed, and you can show this. It's a unitary operator. And in general, for unitary operators, U, which is given by some parameter A, it can be written by an exponential of I times a Hermitian operator times A. Okay, so this is some Hermitian operator. And this is unitary. And the Hermitian operator that gives rise to this unitary transformation, it's the generator of that transformation. Okay. All right. Is that clear? Any questions?
I'll have to go through the stuff again to like ask questions.
Okay.
It's a bit overwhelming, I guess.
Yeah, it is. Yeah, but you did quantum 1+, right?
Yes.
Okay,
The notations are a bit different for me, so.
Yeah, so that's a very good point. And now I come to a place where I want to make connection with the notation that I used in quantum 1+.